In this problem, I am going to demonstrate the use of rotational energy buckets in the energy model with a slight little change with the gravitational ink cartridge. So we have this assembly with a rod and hoop, and they're both of mass m. And this thing is at rest at the top here, and it's going to rotate. So there's a bearing here, and it's going to rotate and come down like at us and end up in this position right about here. So this is about the length of that rod, and here's the hoop here, and it's upside down position. Okay, and so let me just define a couple quantities. I'm going to define the radius of the hoop here. This has a radius of the hoop called r hoop, and that's an h there, and then this length here is L. The rod is a length L to that point right there. Okay, down there like that. So we're going to have this whole assembly start here and rotate. If you imagine coming at us and ending up at this position. Down here, we want to find the angular velocity. So roughly we can say this has potential energy and then it has kinetic energy. So the problem is that we have a composite object. It's composed of two different things. So how do we address the potential energy? So the idea I'm going to use is this. I'm going to look at this as separate entities. I'm going to say the rod's mass is at its center right here, its center of mass, if it's uniform. Okay, and this hoop's center of mass is right here, right there. So when these things fall, they're going to fall to this position here. Their center of the mass of the rod is going to go from here to here. And the center of mass of the hoop is going to go from here to here. Maybe to differentiate, I'll put an X there. That point will go down to there, and so forth. Okay, so if I were to consider the rod by itself, I would say that its reference line is right there. It has a height here. Call it height of the rod. So from its reference lines to its center of mass, that's how far it's going to fall. This is the rod. And then I would say that the hoop's center of mass is going to fall from here to here. So there's a separate reference line to the hoop. Okay, it's going to fall from here all the way down there. Okay, so that's the one mental shift you have to make, is that there's two reference lines, one for each thing. Okay, that's the right there, the height of the hoop, H hoop, if you want to call it that. Height of the rod, height of the hoop. Again, using its centers of mass. So I'll say point A is in the up position and point B is in the down position. So the energy at point A equals the energy at point B. And I have, let's see, I have kinetic energy. I have potential energy. Now, what I'm going to do here is I'm going to say that because there's two different objects moving, I'm going to look at them separately with the ink cartridge model. And then here's our spring bucket if we had some spring. And then over here, our kinetic, our potential, and our spring. So let me write these things down here. U spring, K B, U G, U S. And so we'll have to make sure we have the ink cartridges here, KB, ink cartridges here, and spring. Okay, so let's take a look at what we have here. So at the beginning, if it's not moving, we have no kinetic. We do have potential. The rod has some potential, so we'll have to make sure we get the correct measurements in there. The hoop has potential, all right? So altogether, that's the total potential. No springs involved. This is not going to move translationally. The pivot point right there, the pivot point is not moving. It's fixed, so there's no translation. But we do have a bunch of translational, okay? And then over here, now because each object, the rod and hoop, will reach their respective reference line, there will be no potential at the end and no spring. So what we basically have here, if I take a look at this from an in-cartridge point of view, is I have the mass of the rod times g times the height of the rod, which we define right there, plus the mass of the hoop plus times g times the height of the hoop, okay, equals, now I just have basically 1/2 I omega squared, so it's 1/2 I of everything, I total, which we'll break that down in a second, times omega squared. And we're trying to find omega, okay? So let's see here. The next step, I'll just kind of simplify some things. So all the masses are the same, so the mass, the hoop, and the rod are the same. We also have to figure out this rotational inertia thing. So let's go step by step here. So first I'll say m g h rod plus m, capital M, g h hoop equals 1/2. Okay, so what we have basically we have the rod, which usually is 1/12 ml squared, but we've done some calculations and we know that if it's to its end, it's 1/3 ml squared, the length of the rod itself. Okay, and then this hoop here we can consider a singleton mass at that point. So the rotational inertia of a singleton mass is its mass, m, times how far it is from the pivot point. So how far is it from the pivot point? It's L plus radius of the hoop squared, mr squared, omega squared. L plus RH, because how far is it from the rotation point here? That's L plus RH right there. mr squared, okay? And then, so we can see here, if you take a look at this actually, there's a mass in this term, mass in this term. This mass can be factored out, this mass can be factored out. So it looks like all the masses go away. Okay. And then we are left with, let's see, omega squared over here. So omega squared is equal to, or actually I'll just say omega is equal to this part right here, g h of the rod plus g h of the hoop, which we have to make sure, from our reference line, we have to make sure we get the correct distances here, divided by everything right over here. So if I do this, this is 1/2 times the quantity 1/3 L squared, because the mass canceled, plus L plus RH, the radius of the hoop, quantity squared, and then the angular velocity is the square root of that because we have a square there. So going back and reviewing, so what I basically did is I said, because we have a composite object, I'm going to look at the centers of masses of each of the objects, the rod and the hoop, and see how far they move to their respective reference lines. So I broke that up into the rod's height and the hoop's height, how far their centers of mass are from their reference lines. They all move together, so we have one rotational kinetic energy. Mass is the same, and then this is a composite object, so I got the rod, 1/3 because it's about its end, not its center, and this is a singleton object, and then I canceled mass and solved from there. So that's the basic idea behind solving for the rotational velocity of this situation. In another video, we'll take a look at using the center of mass approach.